Good morning and welcome to this module of Theory of Machines. Before we go into this module, let us briefly review what we have seen in the previous module. In previous module, we have seen that theory of machines, depending on the focus, may be categorized as kinematics, wherein we are interested only in the relative motions in the mechanism, or dynamics, where we are interested in both the relative movements as well as the forces causing them. We have also defined what is a kinematic link and what is a kinematic pair. In this module, we kind of build up on these topics and then try to explain what is relative motion. We'll try to define what is degrees of freedom of a kinematic pair, and then kind of give several illustrations of kinematic pairs in terms of certain animations. And then by the end of this module, perhaps you'll be able to find the degree of freedom of a kinematic pair by inspection. Let us begin this module by recalling that when two links form a kinematic pair, they must always remain in contact while they are moving, that is, while relative motion is occurring. And also, depending on the type of contact, only certain types of motion are possible. We'll kind of start with this note and define what we mean by relative motion. In a kinematic pair, if we fix one of the links and the other link moves while satisfying the conditions A and B mentioned here, we say that the motion of the link is relative motion. I would strongly encourage you to remember this kind of relative motion, definition of relative motion, all through the discussion in this module. Let us begin by looking at several examples of degree of freedom after we go through this definition. Okay, the definition of degree of freedom formally is given as degree of freedom of a kinematic pair is the number of independent ways in which relative motion can occur in the kinematic pair. Though this definition is not exactly the same as the definition given in textbooks for degree of freedom, though essentially both of them mean the same thing, I kind of try to use this definition in trying to bring out what we mean by degree of freedom of a kinematic pair physically. We'll see several examples of kinematic pairs and try to bring out what is the degree of freedom of the examples we see. Let us begin with a simple example here. Okay, let us try to observe the animation carefully. Let me try to animate these. You can see that this is one link with a provision for connection. This is another link for a provision for connection. Both these links are free to move. But once we form kinematic pair by placing one link in such a way that the hole is aligned with the pin, we see that it forms a kinematic pair. While the link is moving, you see that contact is always maintained. Let me try to animate it once again. You have one link with a hole as a provision for connecting. You have another link with a pin as a provision for connecting. This link is taken and placed on the top of the other link in such a way that the hole and the pin are aligned. Once they are assembled in such a way, one of these links, this link is fixed. The other link can move only in one way. It can only rotate about an axis which is same as the axis of the pin. So we call this pair a revolute pair because the link can only revolve about an axis. Because there is only one way in which the relative motion can occur, we say degree of freedom is 1. Okay, and the type of motion is rotation. This link can only rotate about an axis which is the axis of this pin. And thus this pair is called a turning pair or revolute pair, and this pair has a degree of freedom of 1. Let us see an example in real life where this revolute pair is used. Okay, if you carefully notice this is the mechanism of a door hinge. This red link typically is attached either to the wall or to the door frame. This kind of pink link is attached to the door. I would strongly encourage you to take a good look at how the door of a room is attached to the wall. You will realize that it is a revolute pair. Let me try to animate this. Each of these links has 6 degrees of freedom, but once we assemble them to form a kinematic pair, there is only 1 degree of freedom. You can see that this pink link can only revolve. We'll try to see several such animations in the next couple of slides. Okay. This is another schematic representation of a sliding pair. You have 2 links, a green link and a kind of blue link here. Let me try to animate and see what happens when this green link moves in such a way that it always maintains contact with surfaces in this hole. Let me try to animate. You can see that this green link is moving back and forth. Back and forth. As long as contact is maintained, we can say that a kinematic pair is formed between the green link and the blue link. Okay. Also, we can see that again in this case only one type of motion is possible, namely translatory motion. The green link can only slide within the hole. Thus we say that its degree of freedom is 1, because there is only one type of relative motion which is possible, and that relative motion is translation. So you can call this pair as a translating pair, or you can call it a sliding pair. Let us try to see a few more examples. Let us see here an example of sliding pair in real life. Okay, this file cabinet is kind of tilted and it's falling down. Excuse me for that. I should have kept it in the vertical orientation, but let me try to animate it. You can see what this drawer in is doing. It is coming out and going in. So this again is a sliding pair. One is the fixed file cabinet, the second is the moving drawer. These two are moving in such a way that only one type of relative motion is possible, and that relative motion is translation or sliding. And so this is another example of a sliding pair. Let us try to see another example. Here you have 2 links. One, this pink link, which is a plane, okay, lying horizontally. Another one is this blue link. Let me try to animate and see in how many different ways this blue link can move. It's moving across one axis, let us say X, that is one type of motion. It is moving across another axis, Y axis, which is another type of motion. Besides these 2 types of motion, it can stay at one place and rotate about an axis perpendicular to this plane, that is the pink link. So there are 3 different motions possible in this kinematic pair. Okay, while always maintaining contact. Of course, you have to keep that at the back of your mind always. There are 3 types of motion, so the degree of freedom of this pair is 3. Let us try to look at another example. This is a spherical pair, or what we call a ball and socket joint, which is at our shoulder. As you can see, the type of joint that you have at this location is what is called ball and socket joint. Let me try to show an animation of the socket. I'm just kind of turning the socket around so that you can take a good look at it. And then you have another element which is a ball with a long lever attached. Okay, each of these have 6 degrees of freedom, but once you assemble them, take this and put it inside. Okay, stuff it inside somehow so that it cannot come out. Then there are only 3 degrees of freedom, rotation about X, Y and Z. So we say this is again another pair which has 3 degrees of freedom. Sometimes we call this spherical pair also. Let us try to look at another example. Okay. Let me try to animate this and pose this question. Carefully take a look at this animation, okay, and try to answer the questions given here. Okay, see what this is doing. Okay, how the relative motion is occurring. Okay, and then let me also give the answers. Okay, shown here is a nut and a bolt. Okay, we are fixing the bolt and moving the nut. Other kind of possibility is also there, like you fix the nut and move the bolt. An example of such application is a screw jack. So bolt is a fixed link. In this situation we considered nut is the moving link, and we say that the relative motion is helical. To completely understand this, I would strongly encourage you to take a reasonably sized bolt, maybe an M12 or so, M12 bolt or so, and a corresponding nut. Try to move the nut and see. Okay, though it appears that this nut is having two motions, a rotary motion and a translatory motion along the axis of the bolt, the degree of freedom still is 1. The reason is that the rotary motion and the translatory motion of the nut, they are not independent, they are dependent. If you have translatory motion, definitely it should have a rotary motion. Or if you try to turn the nut, if you try to revolve the nut while it is in the pair, it must definitely move along the axis. Because the rotary motion and translatory motion are dependent on one another, we need to count only one of them. That is why we say the degree of freedom of this kinematic pair is 1. The relative motion is helical, and this pair is sometimes called screw pair. Okay. Let me conclude this module by posing two questions. I'll kind of try to animate both these. Try to find out what is the degree of freedom of this kinematic pair as well as this kinematic pair. This blue link is a plane. You have a cylinder here, you have a sphere here. I'll try to animate each one of them. So this you can call a cylindrical plane pair. This you can call spherical plane pair. Let me try to animate the cylindrical pair. You can see here that while the cylinder is moving, it's always in touch with the plane. Let me try to animate this. You can see the cylinder turning about axis 1, which is perpendicular to the blue link. Okay, that's about the relative motions existing in the cylindrical plane pair. Let me try to animate this. See how the sphere is moving. I would like you to carefully observe these two animations maybe a couple of times and find out what is the number of degrees of freedom of this cylindrical plane pair and this spherical plane pair. You have to count how many types of independent relative motions exist in each of these kinematic pairs. Take that as a homework. Okay. With that, we'll try to summarize what we have learned so far. We have seen that relative motion is the movement of one link in a kinematic pair when the other link is fixed. This relative motion can be translation or rotation or a combination of these two. Degree of freedom is the number of independent coordinates which need to be specified to completely describe the configuration of the kinematic pair. The definition we started with and the definition we ended up here, they appear to be slightly different. I would encourage you to think about these two before we meet for the next module. Okay. Further, we have seen a revolute pair, a sliding pair, a plane pair, a spherical pair, a screw pair, a sphere plane pair, a cylinder plane pair. We'll try to explore more about these kinematic pairs and try to kind of give a classification scheme of kinematic pairs in the next module. Okay, thank you very much for staying with us today. If you have any questions or comments or suggestions, please do email them to theoryofmachinesself@gmail.com. Thank you very much and have a good day.